The U.S. aviation industry has long been a beacon of innovation, where groundbreaking ideas are tested and history is made. However, when it comes to hypersonic speed, ambition and determination alone are not enough. Achieving this milestone demands a complete transformation in both mindset and technology. Enter Hermes, a visionary team with a bold mission to introduce the hypersonic quarter-horse, a game-changing advancement in aircraft design. More than just a technological marvel, this aircraft represents a new era of flight, where journeys covering thousands of miles take mere minutes, and speed becomes the ultimate measure of success. When discussing supersonic travel, the legendary Concorde immediately comes to mind. Developed through a partnership between the UK and France, this engineering marvel once soared at speeds of 1,354 miles per hour, Mach 2, twice as fast as standard commercial jets. While groundbreaking, this speed was still far from hypersonic flight, which begins at Mach 5, 3,836 miles per hour, and beyond, a frontier that today's technology is striving to reach. The Concorde's final flight in November 2003 marked the end of an era. On that historic journey, it set a remarkable record, flying from New York to Seattle in just 3 hours, 55 minutes, and 12 seconds, a feat unmatched by any commercial plane since. However, strict regulations on supersonic travel over U.S. airspace forced much of the Concorde's route to pass through Canadian territory, where fewer restrictions applied. Despite its retirement, the Concorde left behind an unmatched legacy, setting speed records and offering an unparalleled level of luxury that remains unrivaled. Yet, the dream of faster air travel never faded. The Concorde's legacy laid the groundwork for future research into supersonic and hypersonic flight, opening new doors to advancements in speed, efficiency, and the integration of hypersonic technology into commercial aviation. Now, an ambitious startup called Hermes is not only looking to succeed where the Concorde left off but also aims to surpass it in every way. Their vision? To transport passengers from New York to London in just 90 minutes, a journey that took the Concorde nearly 3 hours. Leading this revolutionary initiative is CEO A.J. Piplica, backed by a team of elite engineers who have previously worked at aerospace giants like SpaceX and Blue Origin. But they're not just dreaming of the future, they're actively building it, determined to redefine air travel and make crossing the Atlantic in under an hour and a half a reality. At the heart of their mission is the Quarter-Horse, a hypersonic unmanned prototype designed to shatter records, including those set by the legendary State Route 71 Blackbird, the fastest military aircraft ever built. For decades, the State Route 71 Blackbird held the title of the fastest military aircraft, reaching speeds of Mach 3.3, 2,193 miles per hour. But the Quarter-Horse is built to achieve Mach 5, pushing the boundaries far beyond anything the Blackbird ever accomplished. To reach such extreme speeds, a revolutionary engine is needed, one far more powerful than the Pratt & Whitney J58 that powered the Blackbird. Developed in the 1950s, the J58 engine was an engineering marvel of its time, capable of sustaining high speeds at high altitudes. However, it had significant limitations. It couldn't operate efficiently below Mach 2.5 and struggled to decelerate. Recognizing these challenges, Hermes knew that breaking records required an entirely new approach. Rather than relying on existing technology, Hermes developed its own groundbreaking engine, Chimera. Named after the mythical fire-breathing creature, Chimera is a turbine-based combined cycle (TBCC) engine, integrating the strengths of 3 distinct propulsion systems: turbojet, ramjet, and scramjet engines. This hybrid design is a game-changer. Unlike conventional engines, Chimera allows the Quarter-Horse to operate efficiently at all speeds, from takeoff to sustained hypersonic travel. Each type of engine has its strengths and weaknesses, but by seamlessly blending them, Hermes has taken a significant leap forward in the development of reusable hypersonic aircraft. The potential impact of hypersonic technology extends far beyond breaking records. With the Quarter-Horse, Hermes is paving the way for a future where hypersonic speeds become the norm, drastically reducing travel time, enhancing military capabilities, and even opening the door for hypersonic commercial aviation. The aviation industry is on the brink of a revolution, and Hermes is leading the charge. Could this be the dawn of a new era where flights across the globe take mere minutes instead of hours? The answer lies in the power of innovation, and with the Quarterhorse, the sky is no longer the limit. It's just the beginning. A turbojet engine can take an aircraft from a standstill to speeds exceeding Mach 2 with ease. However, once it surpasses Mach 5, it begins to suffer from severe efficiency issues. Despite this limitation, the turbojet plays a crucial role in the initial acceleration phase, propelling the aircraft from 0 to Mach 2 before handing over control. At Mach 2, the ramjet engine takes over. Unlike the turbojet, the ramjet thrives at hypersonic speeds but struggles to function at lower speeds. This limitation makes it ineffective until the aircraft reaches the required velocity for activation. To push the boundaries even further, engineers developed the scramjet engine, designed specifically to operate at speeds beyond Mach 5. While scramjets are highly efficient at extreme velocities, they, too, face challenges at lower speeds, requiring a seamless transition between different propulsion systems. The ability to switch between turbojet, ramjet, and scramjet engines is a complex feat, demanding a sophisticated control system to ensure smooth, uninterrupted operation. In just 21 months and with a budget of $18 million, Hermes achieved a significant milestone with Chimera, successfully demonstrating the transition from turbojet to ramjet. This breakthrough is a major leap in the development of reusable hypersonic aircraft, proving that sustained hypersonic speeds and rapid engine transitions are achievable. In November 2022, the Hermes team successfully executed a real-world transition between turbojet and ramjet, marking a defining moment in the advancement of hypersonic technology. But this was only the beginning. To push the limits even further, Chimera 2 will integrate the Pratt & Whitney F-100 engine, a battle-tested powerhouse used in F-15 Eagles and F-16 Fighting Falcons. The F-100 engine, known for its unmatched reliability and power, can sustain Mach 2.5, 1,900 miles per hour, over extended periods while maintaining stable performance in extreme conditions, an essential trait for hypersonic and reusable aircraft. By leveraging the F-100's sustained power and endurance, Chimera 2 will overcome current speed limitations. Unlike previous engines that suffered performance degradation at high speeds, Chimera 2 will maintain Mach 2.5 without compromise. Additionally, the engine transition system will be further refined, making shifts between turbojet, ramjet, and scramjet more efficient and instantaneous. The combination of the F-100 engine and turbine-based combined cycle (TBCC) technology will lay the foundation for the next generation of hypersonic aircraft. However, challenges remain. Integrating the F-100 into a TBCC system requires precise calibration, while optimizing fuel efficiency and reusability is key to making hypersonic travel commercially viable. Yet, with Hermes' rapid advancements, the future of hypersonic aviation is within reach. Chimera 2 isn't just a leap in speed and performance, it's the dawn of a new era in aerospace innovation. Imagine cutting the flight time from New York to London to just 90 minutes. Is this the future of aviation, or an ambitious dream? Let us know your thoughts in the comments below. Hermes isn't stopping at Chimera. The company is already working on two groundbreaking projects. Designed for high-speed transoceanic routes, Halcyon will travel at 5 times the speed of commercial jets, drastically reducing flight times between major global cities. More than just speed, Halcyon represents a paradigm shift in aviation, combining advanced technology, efficiency, and passenger comfort to redefine air travel as we know it. The potential to revolutionize the aviation and military industries is closer than ever. But before looking ahead to the promising milestones on the horizon, let's take a deeper dive into Quarterhorse, the cutting-edge hypersonic UAV from Hermes, a strategic asset with exceptional potential for both military and civilian applications. Hermes kicked off 2024 with an impressive achievement, completing the ground test for Quarterhorse Mk0, an essential step in testing key technologies and integration capabilities for this advanced aircraft. Following this success, the company announced a bold development roadmap featuring 4 versions: Mk0, Mk1, Mk2, and Mk3, each playing a crucial role in pushing aviation technology forward. Mk0 served as the foundation, designed to test high-tech system integration while evaluating critical features like remote control, radio frequency, RF, latency, and ground processing systems. The tests were conducted at the Arnold Engineering Development Complex, AEDC, in Tennessee, where the team successfully assessed remote control functionality, RF latency, and ground system performance. They also tested how the aircraft would respond in scenarios where communication with ground control was lost, an essential capability for military operations in electronic warfare environments. Ensuring that the autonomous system remains operational even when signals are disrupted is a major breakthrough in the development of hypersonic aircraft. In a remarkable feat, Hermes successfully designed and built Mk0 in just 6 months, completing key test objectives in a record-breaking 37 days. This incredible speed in manufacturing and testing highlights the efficiency of Hermes' development process and their ability to work seamlessly with advanced technologies. The engineering team worked relentlessly to ensure that every system functioned in perfect sync, pushing the limits of rapid prototyping in aerospace development. In March 2024, Hermes unveiled Quarterhorse Mk1, an advanced iteration that introduces significant improvements in hypersonic flight capabilities. While building on the foundation of Mk0, Mk1 enhances key elements such as high-speed takeoff and landing performance, which are crucial for future hypersonic aircraft. This next phase of development will take place at Edwards Air Force Base, one of the most historic testing grounds for advanced aviation technology. From groundbreaking fighter jet projects to UAV testing, Edwards has been at the forefront of aerospace innovation, and now, it will serve as the launch site for Mk1's test flights. Hermes aims for Mk1 to take flight by late 2024, with the goal of proving its ability to execute high-speed takeoffs and landings, a fundamental requirement for sustainable hypersonic flight. While Mk0 and Mk1 utilize the Chimera engine powered by the General Electric J85, the next evolution, Quarterhorse Mk2, will mark a major leap forward by introducing Chimera 2, an upgraded engine powered by the Pratt & Whitney F100. This engine, one of the most powerful in modern fighter aircraft, is already in use on the F-15 Eagle and F-16 Fighting Falcon, delivering exceptional thrust capable of sustaining speeds beyond Mach 2.5 under extreme conditions. Integrating Chimera 2 will not only elevate Quarterhorse's hypersonic flight capabilities but will also improve stability, endurance, and performance at extreme speeds. With Chimera 2, Quarterhorse Mk2 will optimize the transition process between different propulsion systems, ensuring smooth and stable operation across various flight phases, from takeoff to sustained hypersonic speeds. A standout feature of Mk2 is its ability to sustain extreme speeds using proprietary cooling technology, allowing the aircraft to operate more efficiently at high temperatures. This critical advancement will be instrumental in developing future reusable hypersonic aircraft, setting a new benchmark in aerospace engineering. With each iteration, Hermes is pushing the boundaries of what's possible in hypersonic aviation. Their ability to rapidly develop, test, and refine aircraft at an unprecedented pace signals a major shift in the industry. The fusion of cutting-edge technology, rapid prototyping, and strategic military and civilian applications positions Hermes at the forefront of the hypersonic revolution, bringing us one step closer to a future where high-speed flight transforms global travel and defense capabilities. Since May 2024, Chimera 2 has enabled the F100 engine to maintain stable performance at speeds exceeding Mach 3 without overheating, a crucial advancement that allows Quarterhorse Mk2 to execute long-range missions requiring both speed and endurance. This breakthrough not only enhances strategic capabilities but also marks a significant shift toward reusable hypersonic aircraft, reducing operational costs while maintaining peak performance and safety. By pioneering reusability in hypersonic aviation, Hermes is setting the stage for a new era of high-speed flight, where aircraft can be deployed multiple times without extensive maintenance or degradation. Building upon these advancements, Quarterhorse Mk3 is expected to reach speeds of Mach 2.5, with its primary objective being the demonstration of sustained hypersonic flight below Mach 3. A critical milestone for Mk3 is its ability to transition seamlessly from turbojet to ramjet propulsion in mid-flight, ensuring optimal performance across the entire speed range. Successfully executing this transition will prove essential in developing future hypersonic aircraft that can maintain extreme speeds without performance trade-offs. A major goal for Mk3 is to challenge the all-time airspeed record set by the State Route 71 Blackbird, the fastest aircraft ever built. By demonstrating stable flight at hypersonic speeds and transitioning efficiently between propulsion systems, Mk3 will pave the way for the next generation of autonomous hypersonic aircraft, capable of adapting to various operational environments with unprecedented flexibility. The future of hypersonic travel hinges on this breakthrough, as the Mach 4 threshold for quarter-horse Mk3 is expected to redefine high-speed aviation. If Mk3 reaches Mach 4, quarter-horse will not only be an engineering marvel but also a precursor to hypersonic passenger travel. The possibility of New York to London flights in under 90 minutes, a journey that currently takes hours, moves closer to reality, unlocking the potential for a revolution in global transportation. While Hermes has not publicly disclosed an exact timeline for this milestone, aviation experts predict that significant progress could be made by the end of 2025, marking a major breakthrough in the field of hypersonic aviation. With rapid advancements in research and development, Hermes has secured strong backing from NASA and the U.S. Air Force, further solidifying its position as a leader in hypersonic technology. Additionally, the project has drawn the attention of Sam Altman, the founder of ChatGPT, who has provided substantial financial backing through a multi-million-dollar investment grant. This funding is accelerating Hermes' scale-up efforts, attracting widespread interest from the global investment community and technology experts. Sam Altman's strategic vision for future technology aligns with Hermes' ambitions, as he sees the potential for their hypersonic breakthroughs to transform not only aviation but also defense and emerging technological sectors. The question remains, can Hermes exceed expectations and break the SR-71 speed record in 2025? The answer is yet to be seen, but their ambitious journey is one of the most highly anticipated stories in the aerospace industry. Have you ever imagined how the U.S. military might penetrate and destroy the world's most heavily fortified missile bases and nuclear facilities? Consider installations buried deep within mountains, reinforced by layers of thick concrete and protected by the most advanced air defense systems. Iran's underground bases are engineered to withstand conventional airstrikes, designed for longevity and extreme resilience. However, despite these formidable defenses, the U.S. military possesses cutting-edge weaponry and highly sophisticated tactics capable of breaching even the most impenetrable fortifications. In today's video, we take you inside the U.S. military's strategic playbook, exploring step-by-step how these underground missile bases and nuclear sites could be neutralized. This is not just a theoretical scenario, it's a deep dive into the evolution of modern warfare, where precision, innovation, and raw firepower converge to eliminate the world's greatest threats. And don't miss the conclusion, where we'll unveil ultra-modern, highly classified weapons, some of the most controversial and devastating technologies ever developed, that could alter the battlefield in ways never seen before. This is a story of precision, strategy, and unimaginable power, a chilling look at the future of military dominance. Get ready to explore the sophisticated strategies and cutting-edge technology that the U.S. military could use to neutralize Iran's underground missile bases and nuclear facilities. Despite Iran's heavily fortified defenses, the U.S. possesses an advanced arsenal and superior tactics capable of breaching even the most secure bunkers and eliminating critical threats. When discussing Iran's underground bases, their sheer complexity cannot be ignored. Take the Fordow nuclear facility, for instance, an installation buried 260 feet beneath solid rock, far beyond the reach of conventional bombs. Iran has spent billions of dollars reinforcing these underground fortresses, transforming them into near-impenetrable strongholds designed to withstand airstrikes and modern weaponry. These sites house Shahab and Sejal ballistic missiles, capable of striking U.S. and allied bases, including Israel, should conflict arise. However, No matter how formidable these defenses seem, the U.S. military has the means to dismantle them. This is not simply about brute force. It's a calculated combination of intelligence gathering, cyber warfare, stealth operations, and overwhelming firepower. Before an attack can even begin, the U.S. must first locate these underground facilities. Iran employs extensive camouflage systems and mobile missile launchers to conceal these sites, making detection a significant challenge. To counter this, the U.S. relies on high-tech surveillance tools such as the KH-11 reconnaissance satellites and the RQ-4 Global Hawk UAV, which provide precise imaging and mapping of Iran's secretive infrastructure. These aerial assets scan for critical details, identifying entrances, power sources, and underground networks that Iran has carefully hidden. Synthetic aperture radar, SAR, and infrared sensors allow these aircraft to detect buried facilities that traditional satellite imagery may struggle to uncover. In addition to satellite and UAV surveillance, MQ-9 Reaper drones play a crucial role in real-time intelligence gathering. Equipped with optical and infrared sensors, these unmanned systems track activity around key locations, monitoring structural changes and missile movements. On the ground, underground monitoring sensors are deployed to detect seismic activity and other environmental anomalies, providing crucial insights into the layout of these hidden bunkers. However, gathering intelligence is only the first step. Penetrating Iran's defenses requires an unprecedented level of strategic firepower. Interestingly, the first move isn't an airstrike, it's cyber warfare. Once targets are identified, the U.S. could launch cyber attacks to cripple Iran's command and control systems, much like the Stuxnet virus attack in 2010, which severely damaged Iran's nuclear centrifuges. This approach would disrupt Iran's air defense systems, rendering them ineffective before any physical assault takes place. Cyber operations could disable missile guidance software, disrupt radar networks, and interfere with military communications, leaving Iranian forces unable to respond. By shutting down radar detection capabilities, stealth bombers and cruise missiles could approach undetected, allowing for precision strikes with minimal resistance. Beyond electronic warfare, cyber attacks could directly target Iran's missile control networks, making their defensive systems completely inoperable. This tactic would leave Iran vulnerable to the next phase of the assault, air superiority operations. Once Iran's air defense radar and surface-to-air missile systems are compromised, the U.S. would initiate a suppression of enemy air defenses (ISI) operation aimed at completely dismantling Iran's defensive infrastructure. Using a combination of electronic warfare aircraft, radar homing missiles, and precision-guided weapons, the U.S. would systematically eliminate Iran's air defense grid, leaving its military blind and defenseless. Advanced jamming technology would further disrupt enemy communications, making it impossible for Iran's armed forces to coordinate a counterattack. With Iran's defensive layers effectively neutralized, the stage would be set for the final and most devastating phase: high-precision strikes on Iran's most critical underground facilities. The U.S. military's approach to neutralizing Iran's underground missile bases and nuclear facilities involves a sophisticated blend of electronic warfare, stealth aircraft, precision-guided missiles, and next-generation bunker-buster bombs. Once Iran's air defense systems and radar networks have been crippled through cyber warfare and electronic attacks, the stage is set for high-impact airstrikes that can reach even the most fortified underground bunkers. Electronic warfare aircraft like the 18G Growler would play a crucial role in jamming Iran's radar and detection systems, emitting powerful signals to disrupt target tracking and communication networks. At the same time, radar homing missiles such as the high-speed anti-radiation missile HARM would precisely target and destroy Iran's radar installations and command centers, severely reducing the country's ability to coordinate a defensive response. With SAM, surface-to-air missile, systems and radars disabled, U.S. and allied air forces would have a clear path to strike strategic targets deep within Iranian territory with minimal resistance. The F-22 Raptor and F-35 Lightning II stealth fighters, designed for deep penetration missions, would take advantage of Iran's weakened defenses to operate undetected. Meanwhile, Tomahawk cruise missiles launched from warships and submarines would systematically target Iran's air defense infrastructure, preventing any counterattacks from its air force. To further escalate the assault, the U.S. could deploy AGM-183 Air-Launched Rapid Response Weapon, RW, hypersonic missiles, capable of exceeding Mach 5. At such extreme speeds, Iran's air defense systems would have virtually no time to react before these missiles obliterate their intended targets. Beyond airstrikes, electronic warfare aircraft would continue to provide a protective shield for attacking forces. The E-18G Growler, equipped with advanced jamming systems, would disrupt radar and communication signals, further paralyzing Iran's defense networks. Radar homing missiles like the HARM would systematically take out Iran's air defense radars, rendering them blind to incoming attacks. These missiles are designed to lock onto radar emissions, ensuring that enemy radar sites are destroyed before they can detect or respond to an attack. This level of preemptive suppression gives the U.S. Air Force a significant strategic advantage in conducting airborne assaults without major resistance. With Iran's air defenses effectively dismantled, the final and most devastating phase of the attack would commence: the destruction of Iran's underground bunkers and missile silos. The U.S. military possesses a specialized arsenal of bunker-buster bombs, engineered specifically for penetrating and annihilating heavily fortified underground facilities. The most formidable of these is the GBU-57 Massive Ordnance Penetrator, MOP, a 30,000-pound bomb capable of piercing over 60 meters of reinforced concrete before detonation. This makes it the perfect weapon for striking facilities like Fordow, buried deep beneath solid rock. The B-2 Spirit stealth bomber, with its ability to evade enemy radar, would be the ideal aircraft to deliver the MOP bomb deep into enemy territory, ensuring a direct hit on Iran's underground military complexes. Alongside the MOP, the GBU-28, a 5,000-pound penetrating bomb tested in multiple conflicts, would be deployed to target medium-depth bunkers and missile silos. However, the next-generation GBU-72 Advanced 5K Penetrator is what truly revolutionizes deep strike capabilities. This state-of-the-art bomb, designed with enhanced precision and destructive force, is capable of obliterating even the most heavily reinforced underground structures. The GBU-72 employs advanced GPS and radar-guided technology, ensuring it can accurately strike hidden strategic targets with unparalleled precision. Weighing approximately 5,000 pounds, 2,268 kilograms, it features a specially reinforced warhead and bomb casing, allowing it to penetrate multiple layers of concrete, steel, and reinforced materials before detonating with devastating force. This highly advanced weapon system is among the most effective tools for eliminating underground weapons storage bunkers and missile sites, marking a significant breakthrough in modern warfare technology. With the combination of stealth aircraft, electronic warfare, high-speed missiles, and cutting-edge bunker-buster bombs, the U.S. military possesses an overwhelming tactical advantage in neutralizing Iran's underground military infrastructure. The ability to strike hidden facilities with pinpoint accuracy ensures that even the most fortified nuclear and missile sites would be utterly destroyed, effectively eliminating the threat posed by these strategic installations. The GBU-72 Advanced 5K Penetrator is not only a formidable bunker-busting bomb in terms of penetration power, but it also boasts high accuracy due to its GPS-guided and radar-assisted targeting system. This ensures that strategic targets are hit with precision, maximizing the effectiveness of airstrikes while minimizing collateral damage to surrounding infrastructure. Even deeply buried bunkers, reinforced with thick layers of concrete and steel, cannot withstand the sheer destructive force of the GBU-72. Tested in previous military operations, this bomb has proven itself indispensable for neutralizing heavily fortified underground structures. Another devastating weapon in the U.S. arsenal is the thermobaric bomb, which functions by releasing a fuel cloud that, when detonated, creates a massive fireball and an intense shockwave. The extreme temperatures generated by this explosion can reach thousands of degrees Celsius, making it especially effective against underground bunkers, tunnels, and enemy personnel within enclosed spaces. Unlike conventional explosives that rely on shrapnel damage, thermobaric bombs suffocate and incinerate everything within the blast radius, making them ideal for targeting deeply entrenched positions. A prime example of this is the Moab Massive Ordnance Air Blast, commonly referred to as the mother of all bombs. Weighing a staggering 9.5 tons, the Moab is one of the most powerful non-nuclear bombs ever deployed. Upon detonation, it produces a colossal explosion, capable of wiping out entire enemy bases, missile depots, and fortified positions. The shockwave not only destroys surface structures but also cripples electronic systems and underground defenses, paving the way for follow-up attacks. Given its overwhelming impact, some argue that the Moab is the most powerful conventional bomb in existence, a claim that sparks debate among military analysts. In an extreme escalation, the U.S. military could consider deploying bunker-busting nuclear bombs, such as the B-61-12, an upgraded version of the B-61 nuclear bomb. Designed to penetrate thick layers of rock and concrete, the B-61-12 can deliver a nuclear explosion deep underground, completely annihilating hard-to-reach nuclear facilities, missile silos, and command centers. Unlike traditional nuclear weapons, the B-61-12 features a variable yield system, allowing its explosive power to be adjusted between 0.3 to 50 kilotons, depending on tactical needs. What sets the B-61-12 apart is its precision guidance technology, which minimizes collateral damage while ensuring maximum effectiveness against underground targets. Weighing approximately 320 kilograms, it is lighter than most strategic nuclear bombs, making it compatible with modern fighter jets like the F-35 and the B-2 Spirit stealth bomber. However, while its capabilities are undeniable, the use of a nuclear weapon would trigger severe geopolitical and environmental consequences. A nuclear strike could escalate tensions into a global conflict, inviting widespread condemnation, economic sanctions, and potential military retaliation from adversaries. While Iran's underground bunkers are a significant strategic asset, its mobile missile launchers add another layer of complexity to U.S. military planning. These highly maneuverable platforms allow Iran to launch retaliatory strikes from undisclosed locations, making them difficult to track and eliminate. To counter this, the U.S. would rely on real-time surveillance, UAV reconnaissance, and rapid response airstrikes to neutralize these mobile threats before they can be effectively deployed. With a combination of cyber warfare, electronic disruption, stealth airstrikes, precision-guided bombs, and high-impact conventional explosives, the U.S. military possesses the firepower and strategic capability to dismantle Iran's underground military infrastructure. However, the political and global consequences of such an operation remain a critical factor in determining whether such a mission would ever be carried out. Iran's mobile missile launchers present a significant challenge as they can relocate quickly to evade detection. However, the U.S. military is well equipped to counter this threat with armed drones like the MQ-9 Reaper, which can conduct real-time surveillance and precision strikes using Hellfire missiles. With a flight range of 1,850 kilometers and the ability to stay airborne for extended periods, the MQ-9 Reaper is an ideal platform for tracking moving targets. Equipped with advanced sensors and radar systems, it can monitor enemy activity from a safe distance, ensuring that mobile missile launchers are located and neutralized before they can be deployed effectively. The AGM-114 Hellfire missile, a key weapon for drones like the MQ-9, is designed to destroy high-value targets with pinpoint accuracy. Featuring laser or radar guidance, it maintains precise target tracking throughout its flight, ensuring a high probability of impact. With specialized high-explosive anti-tank, heat, and high-explosive penetrator (HEP) warheads, Hellfire missiles can pierce reinforced concrete, armor, and underground structures, making them an effective tool against hardened targets like missile silos and underground bunkers. To further enhance precision strike capabilities, the U.S. military could deploy hypersonic missiles, which travel at speeds exceeding Mach 5. At such velocity, these weapons are nearly impossible to intercept, ensuring that Iran's mobile launchers and other strategic assets are eliminated before they can reposition. Beyond aerial and missile-based attacks, U.S. Special Forces such as Delta Force and Navy SEALs would play a crucial role in the campaign. These elite units specialize in stealth infiltration, sabotage, and high-risk missions deep within enemy territory. Their expertise would allow them to disrupt Iran's military coordination by targeting radar stations, communication hubs, and strategic facilities. They could also plant explosives in underground bunkers and missile storage sites to cripple Iran's defensive infrastructure. By guiding airstrikes with laser or GPS markers, they would ensure precision targeting while minimizing collateral damage. Additionally, special forces could weaken Iran's resistance by sabotaging weapons stockpiles, fuel depots, and supply routes, creating logistical challenges for their forces. By working in close coordination with air and naval forces, special forces would help ensure the success of a precision strike campaign, limiting Iran's ability to respond effectively. With a combination of real-time intelligence, high-speed weaponry, and strategic sabotage, the U.S. military would be able to neutralize key threats and minimize risks while maintaining operational dominance.